April 16, 1946. White Sands Proving Ground, New Mexico. The desert air still held the night's chill when a grey cylinder taller than a 5-story building began to shiver on the pad. Frost blooming along fuel lines while a crew in Army khaki and General Electric coveralls moved with rituals learned from enemy manuals. The rocket on launch complex. 33 was a captured German A4 the Reich called the Victorious, assembled from crates shipped through New Orleans and the Brooklyn Navy Yard, fueled with ethanol and liquid oxygen, and aimed not at a city but at the upper atmosphere. Minutes later, a turbopump scream cut through the basin. A yellow-white flame sheeted across the ground, and the projectile tore skyward past the Organ Mountains until it vanished into a pale morning. For the Americans on the blockhouse phones, the first successful USV to launch was not a stunt, and it was not a trophy. It was a controlled encounter with a weapon whose wartime existence had been understood mostly through radar tracks, bomb damage reports, and fragments in London streets. Measured by thrust, speed, and reach, the A4 was an artillery piece fired across the threshold of space. Measured by what it implied a ballistic trajectory no fighter could intercept. A guidance problem solved with gyros and integrators. A production system, indifferent to weather and pilot sit, signaled that the grammar of war had shifted from horsepower and propellers to turbines, chemistry, and computation. The vehicle those engineers watched was about 14 meters long, with a diameter of roughly 1 meters at its widest point, and a takeoff mass that could exceed 12 metric tons depending on instrumentation. Its engine delivered on the order of 245 kilonewtons of thrust at sea level, pushing it through transonic regimes to roughly Mach 4 or more as it arced toward apogees, well above 30 kilometers in combat use, and over 100 kilometers in the experimental profiles now being flown. In 1944 and early 1945, the same shape had carried a warhead of around a metric ton against London, Antwerp, and Liege, landing without warning in a supersonic dive that made all previous notions of civil defense feel quaint. But for the men and women at White Sands in April 1946, the payload was a suite of instruments. Geiger counters would ride where Amatol once sat. Vacuum-sealed cameras would look where proximity fuses had been, and the point of impact would be a telemetry tape and a set of normalized numbers, per second and per kilometer rather than a crater's diameter. The program that gathered those crates and people together had multiple names and overlapping boundaries. The Army Ordnance Department called the launch series Hermes and retained General Electric as its prime contractor for integration and test. The transfer of German technical personnel first to interrogation camps in Europe, then across the Atlantic to Fort Strong in Boston Harbor, and finally to Fort Bliss and White Sands was folded into what became widely known as Operation Paperclip. Contemporary Army counts indicate that the United States obtained parts sufficient to assemble on the order of 60 to 70 testable V-2 airframes, and records show that between 1946 and 1952, the range conducted roughly 67 522 launches of varying configurations, some failing at ignition or in ascent, many reaching useful apogees. As for personnel, initial transfers numbered in the low hundreds, later growing to several hundred over the late 1940s as specialists in propulsion. Guidance, structures, and aerodynamics were brought under contract or military custody. The story of how a weapon that terrorized civilians became an American instrument begins months earlier in collapsing Germany. In May 1945, a team led by Werner von Braun surrendered in Bavaria to the U.S. Army, their decision shaped partly by the simple vector of geography and partly by calculation. They were fleeing eastward encirclement in Thuringia and knew that Soviet forces were converging on Nordhausen, the underground Mittelwerk where the A4 had been assembled. American ordnance officers, aided by technical intelligence units, followed documents, rail spurs, and testimony to storage sites in the hearts and to launch battalions that had dispersed equipment in the field. Locomotives hauling captured components rolled west to Antwerp and ports on the Channel. Naval freighters carried fins, tanks, turbopumps, and guidance platforms across the Atlantic. At White Sands, the Army built a pad and blockhouse in a vast weapons range carved out of New Mexico scrub. A geography chosen because it offered thousands of square kilometers of uninhabited downrange. Fort Bliss housed security and administrative functions. On the other side of the state line, the range offered the vertical lab that wartime Europe never could. The first weeks on site taught the Americans why the German machine had been so hard to counter and so difficult to sustain. The V2 was not a single thing so much as a system of systems. The propellant feed train demanded precise timing and temperatures. The guidance packager stabilized platform with rate gyros feeding an analog computer required careful alignment to a local vertical. The engine chamber, a steel bell with internal cooling passages, wanted tolerances that pushed U.S. machine shops used to mass automotive production into a new vocabulary. A single leaky gasket at cryogenic temperatures could ground a launch. The Germans on base, now living under guard and working under supervision, explained procedures through interpreters, chalk sketches, and, often enough, hand signs. Their instructions were technical. Their presence was political. A few months earlier, many of these men had been members of a regime that used forced labor at Dora Mittelbau, with a death toll measured in the tens of thousands across the life of the program. Estimates vary. Historians place the number of prisoners who died building V2 South between roughly 10,000 and over 20,000 when including those killed in evacuations and related camps. The engineers on the American side were not blind to this. Memos and diary notes from ordnance officers and GE managers registered the ethical dissonance of learning from technology that had consumed so many lives. Operationally, however, the United States confronted the fact that the A4 was a proof of principle for something larger. If a 14-meter ballistic vehicle could carry a ton across roughly 300 kilometers in 5 minutes, then an upscaled derivative could, in principle, carry a smaller payload much farther given better propellants, lighter structures, more efficient engines, and improved guidance. If its terminal velocity in thin air was beyond the reach of any propeller fighter, and at the limits of early jets, then the defense problem shifted from interception to warning and hardening. Those are not abstract shifts. They rewrite procurement, doctrine, and the line between theater and homeland. To understand how startling that first White Sands launch felt, normalize the numbers to rates and to what was then considered state-of-the-art. A single V2 engine burning roughly 125 kilograms of propellant per second for around 60 to 70 seconds created an impulse that no aircraft piston engine could match. The best Allied fighter engines in 1945 produced on the order of 1,500 to 2,000 horsepower each. Useful for sustained flight, but offering thrust measured in kilonewtons only, with propellers biting air, not raw exhaust. A V2 did not contest the air. It bypassed it. Mean flight time to target in operational use was measured in minutes, not hours, across a footprint that had taken bomber streams thousands of sorties to saturate, where a heavy bomber like a B-17 carried about 2 to 3 tons of bombs over 1,000 kilometers with a crew of 10 and hours in transit. A V2 delivered around 1 ton, over a third of that distance, with no crew and a sortie time under 10 minutes. In return, accuracy was poor, with circular error probable measured in kilometers rather than meters for 1,944-45 battlefield use, which made it a terror weapon rather than a precision instrument. The White Sands program aimed to trade explosive weight for knowledge, because knowledge could be refined into accuracy. The April shot was only a beginning. Over the following months, teams instrumented the vehicles with radiometers to study atmospheric absorption, pressure sensors to map density profiles above the range, and sealed cameras to record cloud decks from near space. On October 24, 1946, one of those V2 South carried a 35mm camera to over 100 kilometers and returned a photographic strip that became, in practical terms, the first image of Earth taken from space. A black and white patchwork of cloud and desert that telescoped the globe into the viewfinder of a rocket designed for war. The normalization that mattered to the ordnance planners was not aesthetic. It was about rates of learning per launch and per year. Pre-war rocketry in the United States, powered by the work of people like Robert Goddard in New Mexico and Massachusetts, had demonstrated the feasibility of liquid propellant rockets in smaller configurations. What White Sands gave the Army and later the Air Force was a cadence, dozens of large vehicles in a half-decade, sufficient to move from treatment of the rocket as a mysterious artifact toward treating it as a platform with known failure modes and improvable subsystems. If 10 launches in a year produced usable telemetry 9 times and structural data 6 times, then one could justify instrumented variants and the funding lines that created them. If a new nozzle geometry raised effective specific impulse by a few seconds when corrected for atmospheric conditions, then the same budget line could argue for machining capacity in Huntsville down the road. The realization that the war had entered a new level came not from a single epiphany, but from converging lines on graph paper. Speed versus altitude during boost, guidance drift per minute as a function of platform isolation, thermal stress accumulation per firing. On those terms, the V2 was a data generator. Each shot replaced one guess with one distribution. On the policy side, the impact was immediate and uncomfortable. The United States had demobilized millions of men in 1945, converting factories back to cars and appliances. But the test profile of a captured German missile in April 1946 signaled that demobilization would not resemble the aftermath of 1918. The Office of Scientific Research and Development handed projects to the new Office of Naval Research and to Army Air Force laboratories, and the Joint Research and Development Board tried to keep an index of who was doing what across rockets, electronics, and nuclear work. In the V2 case, the split of roles was already political. The Army, jealous of its ordnance heritage, argued that ballistic missiles were land-based artillery scaled up, while the Air Force, even before its 1947 independence, argued that anything delivering payloads across continents belonged to air power. That doctrinal argument, running through committee rooms and budget hearings, was the bureaucratic echo of a physical fact. The engineers were plotting in the desert. Ballistic arcs ignore borders and services. In parallel, the United States knew that the Soviet Union had seized launch hardware, drawings, and German specialists as well. Across 1946 and 1947, Soviet engineering bureaus unpacked their own V2 derivatives, leading to the R1 and A4, copy that first flew in 1948, and then to incremental improvements that ultimately fed the R7, the world's first intercontinental ballistic missile and orbital launcher. American security memoranda from the late 1940s treated these timelines as threats expressed in years rather than divisions. If a nation could move from a 300-kilometer missile in 1945 to a 5,000-kilometer missile a decade later, then the geometry of the Western Hemisphere's safety was altered by a function of range growth per year. Compute the difference. A bomber stream might require hours of warning and hundreds of radar plots. An ICBM compresses decision time to tens of minutes. That compression was what April 1946 whispered. The war of throughput, sortie rate, and convoy protection had not ended. It had been joined by a war of exponentials in range, speed, and yield once nuclear physics met controlled rocketry. The technical work that made those exponentials tractable was often unglamorous. In the blockhouse, Army officers learned how to translate German pre-launch checklists into English, not only linguistically but culturally, breaking tasks into sequences that fit American safety practices. General Electric supervisors created toolroom inventories so that turbine vanes and injector plates could be matched to serials rather than to a technician's memory. The propellant team learned that ethanol concentration mattered for cooling as much as for combustion. Even fractional differences altered wall temperatures enough to affect life cycles. So they wrote procedures that pinned concentrations to ranges and timed chill-downs to minutes rather than to instincts. Guidance technicians pulled apart the German integrator and found that some error terms could be reduced not by adding complexity but by machined precision on gimbal bearings. Each of these interventions converted the V2 from a fielded prototype into a teachable architecture. The Americans began to re-engineer components with U.S. manufacturing techniques, laying the groundwork for vehicles like Redstone in the 1950s, which reused the V2's conceptual skeleton while altering materials, engine cycles, and guidance brains. A seal of honesty belongs here because wartime secrecy and post-war publicity sometimes distort the sequence. American rocket work did not begin with captured German hardware. Goddard's rockets flew in the 1920s and 1930s, and Navy and Army groups pursued solid fuel and liquid fuel experiments in parallel during the war. Likewise, the captured German team was not a monolith. Members brought varying levels of expertise and responsibility, and their assimilation into U.S. programs involved security vetting, layers of euphemism, and political compromise. What White Sands did was to collapse lead times by giving American teams access to a full-scale flight-proven system, whose flaws were as instructive as its strengths. Consider accuracy. The V-2's wartime circular error probable was measured in kilometers. For a terror campaign that sufficed for battlefield interdiction or strategic strikes with scarce payloads, it did not. The White Sands flights, heavy on instrumentation and light on warheads, let engineers plot error sources by contribution per second of flight, platform drift during boost, aerodynamic perturbations during transonic passage, and guidance response delays near engine cutoff. Strip away a quarter of the error by refining platform isolation, shave another fraction by tuning control loop gains, and accept that the rest required new sensing altogether radar or celestial references. Each % reduction was a program decision, a budget line, a test article. By 1947 and 1948, the Americans were using V2 South 2 loft-sounding payloads that measured cosmic rays and solar UV above the atmosphere, generating datasets new to science and, not incidentally, training a generation of technicians in cleanroom habits and recovery logistics. The first photograph of Earth from over 100 kilometers, taken in October 1946, became a public symbol of peaceful application. But range logs show that the majority of shots focused on performance curves, component life, and failure analysis. Normalized in terms of learning. A single successful flight could yield tens of thousands of telemetry samples per second across multiple channels. An order of magnitude more insight than a static firing alone. Failures, too, paid dividends. A turbopump rupture, early in a 1947 sequence, forced a redesign in bearing materials. A guidance oscillation near engine cutoff, detected by post-flight analysis, prompted a change in damping that reduced pitch excursions by measured degrees. Every corrective action could be expressed as a percentage improvement per flight hour and per dollar spent. A language that translated to the Pentagon became persuasive. For the people on site, the psychological shift was as real as the engineering. In the war that had just ended, the United States had industrialized victory with Liberty ships, trucks, and bombers built by the hundreds of thousands. At White Sands in 1946, the unit of measure was no longer the number of rivets a line could set in a day, but the number of meters per second a guidance integrator could keep true while the horizon fell away at a kilometer per second. The factory logic that had overwhelmed the axis still mattered, but it was now braided with laboratory logic, in which a new alloy could be as decisive as an assembly line speed-up. When the April vehicle cleared the pad and arced southward, the blockhouse plotted a trajectory with grease pencil across a plexiglass board. For the first time in American hands, that curve was not hypothetical. It represented a type of weapon that, scaled and refined, would cross oceans in minutes, carrying more than the tonnage of Amatol the Germans had used. Even in 1946, ordnance officers were writing staff notes about what would happen when a fission device, or, later, a fusion primary, could be mated to a guidance package that put it within a kilometer of aim point after a flight lasting less than half an hour. Those were not procurement fantasies. They were extrapolations grounded in the data rising off the desert. The launch cadence that followed in 1946 and 1947 built institutional muscle. Recovery crews learned to chase impact points across Jornada del Muerto scrub, coordinating by radio and improvising when parachutes failed to deploy. Instrumentation crews learned to harden payloads against vibration spectra, characterized in GS per hertz. Where the teams learned to feed high-altitude winds into pre-launch models to bound dispersions as deviations per meter per second of crosswind. By normalizing each discipline's contribution to the variance in impact error, Managers could decide where to spend the next dollar for the next percentage point. Those methods: variance reduction, failure mode, categorization. Design of experiments were not unique to rocketry, but rockets compressed timelines and raised stakes enough to make them urgent. Meanwhile, outside the range fence, the public and the press tried to decide what the V2 meant. For citizens who had lived through blackouts and casualty telegrams, the object on the White Sands pad was both trophy and omen. Newsreels lauded scientific exploration while eliding the uglier provenance of the hardware. Editorial writers asked whether America should be learning from men who had served a criminal regime. Congressional hearings probed Paperclip selection criteria, and the degree to which anti-communism had become a solvent for past affiliations. Inside the program, engineers tried to keep the argument empirical. Here is the data per flight. Here is the improvement per quarter. Here is the path from a German artifact to an American system. The path, they argued even then, ran through vehicles that would bear new names: Redstone, then Jupiter and Atlasand. It ran through ranges that would move from the New Mexico desert to Florida's Atlantic coast. The April 1946 launch was not the birth of that path, but it was the first time the United States watched a large liquid rocket of proven wartime pedigree behave under American procedures, American instrumentation, and American aims. In the ledger that the Army kept, the shot's value lay in numbers and in a demonstration that men trained on. Carburetors and propellers could learn to think in pumps and nozzles. That gunnery tables could give way to guidance algorithms. That sortie might no longer mean a crew to debrief, but a stack of telemetry rolls to analyze. The realization was not theatrical. It settled on the blockhouse like dust. A rocket that ignored the sky's defenses had flown on their range and given them data by the 1,000 per second. Scale that, refine that, and the assumptions of distance and time that had protected continents would erode. In that sense, the first V2 flight at White Sands read like a preface. The chapters it introduced would span a dozen years, from Army rockets launching America's first satellite in 1958, to Air Force missiles that shrank flight times across oceans to under half an hour. The engineers watching the streak vanish into the morning did not yet know the names of Cape Canaveral pads or the acronyms of early warning systems. But they could read the curve that traced across their plotting board and see that artillery had lifted clear of the air and was learning to write its own trajectories into the upper atmosphere. They had tested a captured weapon and found, in its equations, the outline of a future war that would be fought in laboratories, assembly bays, and command centers where minutes mattered more than miles, and where the first move would be a launch that no human could chase. The shift from artifact to architecture accelerated with a hybrid experiment that would have seemed like science fiction. To a bomber pilot returning from a 1945 mission, engineers stacked a slim American-sounding rocket on the nose of a V2 and called the series Bumper WAC. The German booster providing the brute impulse and the American upper stage exploiting the near vacuum. Within 3 years of the April 1946 shot, one of those combinations climbed past 390 kilometers, more than triple the operational apogee of a wartime A4, and higher than any human-made object had flown to that date. An altitude record that translated directly into equations for staging efficiency and guidance handover. That number mattered not for bragging rights, but because it proved a principle. Add stages and the reachable world changes by orders rather than increments. In the blockhouse culture that formed around these flights, success was measured by how much unknown was converted into parameter ranges. Crew chiefs, who had come from aircraft maintenance, learned to think of engines, not in hours between overhauls, but in cumulative, thermal cycles before creep or burn-through. Instrumentation teams translated failure into the vocabulary of spectra, discovering that the V2's structure rang at identifiable frequencies that could be damped or avoided in the design of mounting frames. Guidance technicians began to replace German analog integrators with American-built components, introducing cleaner signals and different failure signatures. Each improvement could be entered in a logbook with a denominator of flights, weeks, or dollars, a discipline that would later allow senior officers to argue that money spent on rocketry bought time in a way that money spent on traditional airframes did not. The men who had assembled the A4 in underground Factories were now ringed by American guards and working under American managers. Their roles circumscribed, their knowledge mined, and gradually exceeded. Records from the range and from Fort Bliss reveal that, as the Americans rewrote procedures, the dependence on German know-how fell month by month. When a turbopump seized in a 1947 static test, the redesign process was driven not by memories from Mittelwerk, but by U.S. materials, labs correlating metallurgical reports to operating temperatures. When control loops oscillated near engine cutoff, the correction came from American control theory, some fresh from graduate schools, who tuned gains using data sampled at rates far beyond anything available during the war. This transfer of initiative was as much cultural as technical. The A4 had been birthed in a system that tolerated high waste and high mortality to reach a wartime objective. The emerging American program insisted on statistical control and repeatability, because the stakes were moving from a terror weapon to a strategic infrastructure. By 1947, the Army's Redstone arsenal became the gravitational center for this new work, gathering design authority that would culminate in the Redstone missile at mid-decade. Redstone looked like a longer, cleaner descendant of the V2, because in many ways it was. But the lineage hid revolutions, different propellants, a redesigned engine cycle, and guidance systems that blended gyroscopic stabilization with radio updates in test phases. In parallel, the Air Force drove its own branch of the family tree toward longer legs, pushing liquid oxygen and kerosene engines sized for intercontinental range. The Navy explored sea-based options, constrained by submarine hulls and ocean logistics. The services sometimes fought on paper over who owned which horizon, but their arguments acknowledged the same geometry. Ballistic arcs had introduced a regime in which warning time would be measured in tens of minutes, and in which a warhead's speed would compress politics. The public images from White Sands were carefully curated. Newsreels showed the October 1946 Earth photograph, a grainy ribbon of cloud and land that let audiences imagine exploration rather than annihilation. Range reports, internal to the government, were colder. They plotted probability contours for where a warhead would land as functions of platform drift, winds aloft, and guidance errors. They noted that if a ballistic vehicle of the V2's class could carry 1,000 kilograms 300 kilometers, then a larger vehicle could, in principle, carry a fraction of that weight thousands of kilometers. They observed that a fission device engineered into ruggedized packaging could replace high explosive, and that the physics did not care about borders. Those observations were not speculative. They were the quantitative outline of what, a decade later, became the strategic missile age. The Soviet Union traced the same outline with different tools. Red Army teams and specialists from Moscow reached German sites in 1945 and ferried hardware and personnel east, setting up their own test areas and design bureaus. Their first copy, the R1, flew in 1948 with performance similar to the A4, and successive designs lengthened the range and weight until the R7, a clustered vehicle, demonstrated both intercontinental capability and, in October 1957, the ability to loft a satellite. The American reaction to that launch was political theater and administrative reorganization. But under the noise, the technical base built in New Mexico and Alabama carried through. When Explorer 1 rose in January 1958 on a Juno I itself, a Redstone variant with upper stages, it did so with integration habits and failure analysis reflexes forged in V2 shops and on desert pads. Explorer 1's scientific payload discovered a belt of radiation circling the planet, an early proof that the same rockets that had rewritten war could also extend knowledge. 4 officers who had survived 1944 logistics and 1945 firestorms. This duality made the new level of war both terrifying and undeniable. Normalized to human time, a bomber campaign unfolded over months and offered leaders opportunities to adjust. A missile campaign, once within reach, would compress decision windows to half an hour and leave no room for increment. That compression began as a chalked curve on a blockhouse plotting board in 1946, and ended as a line on a wall map in command centers, the line shortening with every improvement in engine efficiency and structural mass fraction. Doctrine had to bend. The Army anchored in artillery tradition, could argue that ballistic missiles were extreme artillery. But artillery does not change national policy with a single shot. The Air Force, defined by crews and aircraft, could argue that only airmen could manage global reach. But the rockets they needed carried no pilots. The Navy, obsessed with mobility and second strike survival, imagined missiles that rose from the ocean. In the early 1950s, those doctrines clashed in hearings and memoranda. But budgets began to reflect the same acceptance that the White Sands engineers had reached during their first months with A4 hardware. A nation's survival would soon be tied to guidance accuracy, metallurgy, cryogenic handling, and the reliability curves of complex machines that left the atmosphere. There was also the problem of defense. A V-2 could not be intercepted by any aircraft of 1944 or 1945 vintage because it outran the air. Could a future missile be intercepted by another missile? Early tests with radar tracking and fast point defense guns suggested that terminal interception against a supersonic, ballistic target was barely plausible at small scales. Against an object descending from hundreds of kilometers at several kilometers per second, the math grew unforgiving. The United States and its allies built early warning nets across the Arctic, strung radar lines from Alaska to Greenland, and created command centers to filter false alarms from real ones. Those investments were futures priced against physics lessons that had been inscribed by a German rocket on an American range. The scale of investment can be normalized to research productivity as well as $2. In 1946, a single V-2 flight might yield tens of channels of analog telemetry recorded on film or wire. By the mid-1950s, test articles returned data across hundreds of channels, digitized and telemetered to ground stations. Failure modes that had taken a dozen flights to isolate in 1947 could be caught in 2 or 3. A stage separation that had been modeled heuristically could be filmed and implemented, its outcomes bounded by standard deviations rather than hunch. That acceleration in learning loops made procurement risk tolerable and allowed design teams to iterate without waiting calendar years. When those habits were applied to vehicles with names like Atlas, Titan, and Polaris, the cycle from drawing to pad again shortened in ways that would have been unthinkable in the era of piston engines and propellers. The realization at the core of the April 1946 launch thus has two faces. One is the obvious one, the face that stares out of photographs and newsreels, a spear of steel and fire leaving the atmosphere. The other is quieter, the accumulation of procedural knowledge that tells a country how to build, test, and field machines that demand perfection because their margins are thin. That knowledge was purchased with money and time, but also with ethics and memory. The White Sands engineers could not look at their flight articles without remembering that the V-2 program's wartime industrial base was a tunnel complex where prisoners died in darkness. Range commanders and civilian managers wrestled in memoranda and in choices. With the contradiction of building a future on the bones of a past, they did not resolve it. They recorded it and moved forward because the threat curve rising from the east did not wait for moral closure. The murder rate inside Dora did not lower the apogees over Capastin Yar. As the 1940s closed, the line from the desert to the future grew clearer. The Army's Redstone would serve as the booster for an American astronaut's suborbital flight in 1961, an event of exploration that also served as a demonstration of guidance and re-entry, both relevant to war. The longer-range Jupiter, born from the same intellectual stock, would become an intermediate-range missile deployed overseas as part of alliance politics. The Air Force's Atlas would reach intercontinental range and become operational in 1959. A machine whose graceful stainless steel skin hid the same fundamental truths plotted in grease pencillet. White sands, burn time, specific impulse, mass fraction, guidance error. The Navy's Polaris would break the surface and carry a warhead from a submerged platform. A concept that owed everything to the recognition that mobility and stealth were the only answers to compression of time. None of those names could have been spoken with confidence in 1946. All of them were implicit in the equations that engineers were turning into curves during that first summer of flights. The way the war had entered a new level became unmissable on a day that had nothing to do with the desert. On October 4, 1957, a Soviet launcher lifted a polished sphere into orbit. At one level, the payload was elementary, a beeping radio that crossed the sky every 96 minutes. At another, it was the proof that equations written on white sands, plotting boards, now governed the whole planet. If one power could place a sphere into orbit, it could place a cone on a trajectory that crossed an ocean in half an hour. The answer to that challenge sprang from the same habits the Americans had been building with V2 South. Multi-stage engineering, high-speed telemetry, standardized checkout, and a culture of failure analysis that was patient enough to find root causes and ruthless enough to act on them. The public debate that followed the beeps was loud, but inside the ranges and labs the response was a continuation, a faster cadence built on a 10-year apprenticeship. The end of the beginning arrived in January 1958, when Explorer 1 rose and returned its data on radiation belts. A scientific surprise that also validated the upper stage stacking and guidance refinements the program had been perfecting. The men and women who had stood near Launch Complex 33 in April 1946 would have recognized the arc and the discipline. They had not built Explorer 1 directly, but they had taught the country how to build things like it. The bridge from terror weapon to scientific instrument was not an absolution, but it was a fact. In the decades that followed, the same mathematics would carry crews to orbit and to the moon, and would, in quieter silos and patrol areas, keep missiles on alert under a logic of deterrence alien to 1945. The moment of recognition can be placed back in the desert. It was not the flame or the roar, but the silence that followed when the vehicle had vanished, and the only sounds were the fans in the blockhouse and the click of a relay as a recorder rolled. The officers and civilians looked at each other, and then at their plots. Some were thinking of budgets, some of careers, some of the men they had buried in Europe and the Pacific, some of families at home. All of them were looking at a series of numbers that, when normalized per second and per kilometer, added to one conclusion. The next war, if it came, would be fought on trajectories that ignored weather and borders, with machines that demanded new disciplines, with warning times too short for old habits. In that sense, the captured rocket they had just launched had told them something simple and immense. It said that distance had been demoted and that speed had been promoted, that chemistry and metals and gyros would soon set the pace at which nations lived. It said that the grammar of war had been edited by physics, and that the only way to survive in that grammar was to learn its rules faster than an adversary. That lesson became policy, posture, and, in the best moments, exploration. The legacy of the first American V2 flights is therefore not a single photograph or a single vehicle lineage. It is a change in how a country thinks about power and time. It is the willingness to measure rather than to guess, to admit error bars and then shrink them, to accept that a weapon once aimed at cities could become an instrument pointed at the sky, and that from its data one could derive both fear and knowledge. From April 1946 onward, engineers in the desert and managers in Washington began to live by that clock. The hands moved quickly. The curve they plotted that morning has not stopped drawing itself across the world. As we approach the end of our remembrance today, we're grateful you listened to this full story with us, and we're glad our archive has nourished your heart and soul. War stories have probably also marked your family's life in some way, haven't they? Maybe you wore the uniform yourself, or perhaps someone you loved did. Your father, a grandfather, or even an uncle. If so, we'd like to invite you to add another chapter to this record. Share with our community a war story that resonates in your family in the comments below. It could be a family tale, a saved letter, a lesson learned on a flight line, or in a muddy field. Anything you want. Tell us from where and what time are you listening to this message. This contribution helps to grow and keep our community together. We can't let these incredible stories be lost in time. The World War II Archives channel was created to honor and preserve these memories. Finally, if this resonates with you, we invite you to subscribe and perhaps share it with a friend who also recognizes the importance of these tales. Stay tuned so you don't miss the next one of our lost archives yet to come.